All right, welcome back. Let's continue our discussion about limits at infinity. So the practical application of limits at infinity is that, as I mentioned in the previous video, it allows you to find horizontal asymptotes. Now, as you see here in the text, it's possible that you could have two horizontal asymptotes at most. In other words, what that means, you could have two horizontal asymptotes, 1 or 0. Like, think about it. As we saw a few videos ago with polynomials, polynomials have these nice smooth curves, stuff like this. Polynomials don't have any horizontal asymptotes. They will always have limits at infinity that are equal to either positive or negative infinity. It's also possible that you could have all kinds of crazy stuff where there's no horizontal asymptote. Think about say sine or cosine. So sine kind of goes like this forever. A limit at infinity means that you approach a specific y value, a single specific y value, as x either increases without bound or decreases without bound. But sine, as x increases, just always bounces back and forth between +1 and -1. And as x decreases, always bounces back and forth between -1 and +1. It's never approaching a single value. Students sometimes mistakenly say, sine approaches plus or minus 1. But that doesn't really make any sense, really, because it's bouncing back and forth, yeah, but it's not approaching +1 or -1. It really makes no sense. Plus, a limit, of course, has to be a single value. Okay, so limits, you can have two limits at infinity. Therefore, you can have two possible horizontal asymptotes. And basically, the idea is that if you find a limit that equals a finite number, well, then you found a horizontal asymptote. If you have a limit at infinity that equals an infinite limit, well, then that's not a horizontal asymptote because it's not finite. But if you find a finite limit, well, then you have found a horizontal asymptote. So we just have 4 more examples here. The difference here being we want to, for each of these, consider both limits because we want to identify the horizontal asymptotes. And since there's 2 possible ways you can find a horizontal asymptote, that is, consider the limit as x goes to infinity, and we have to consider the limit as x goes to negative infinity. So we could get the same answer, we could get different answers, we could get D and E in both cases. So we'll have to see. Let's take a look. All right, so with example A, we want to look at the 2 limits. The limit as x goes to infinity of our function 10 over 2 plus e to the negative x. And then we also want to look at the limit as x goes to negative infinity of the function 10 over 2 plus e to the negative x. Okay, let's see. Now with these, at least example A and B, examples A and B don't really have any specific technique to them. C and D, we're going to use that technique from the previous video about dividing strategically. But here we don't really have a special technique. The only thing I'd probably do with example A, with the first limit, is to rewrite it slightly and say this is equal to the limit as x goes to infinity of 10 over 2 plus, now what's e to the negative x? That's 1 over e to the x, right? Now the reason I would say it's advantageous to write it like that is because now you can see that if you only consider this little fraction, if you take here, let's apply the properties. Let's just not let's do this in a formal sense. Let's apply the quotient property and the sum difference property, and say this is the limit. Oh, sorry, quotient property. So we're gonna have a quotient limit as x approaches infinity of 10 over the limit as x approaches infinity of 2 plus the limit as x approaches infinity of 1 over e to the x. Okay? Now, clearly, we have 2 constants. So that top limit goes to 10. this limit goes to 2. What about this limit? Well, then the numerator is 1, the denominator is variable, and that means the denominator is growing while the numerator is constant, so that overall has to go to 0. Has to go to 0, okay? And so what do we get? Here, let's first of all, let's move this down a little bit. What do we get? We get, well, 10 over 2 plus 0, so we get 5. We get a finite answer. So the limit, of course, is equal to 5, but since we got a finite answer, that tells us that y equals 5 is a horizontal asymptote. So there's one horizontal asymptote. Now let's consider the other limit. So the other limit that I had to erase just a moment ago would be the limit as x approaches negative infinity of 10 over, let's start over, 10 over 2 plus e to the negative x. Okay? Now, on this one, I don't think I'm going to rewrite it. I don't think I'm going to rewrite it. Why? Because if I think about what's happening here is that if we take the limits individually, we get a quotient, we get the limit as x approaches negative infinity of 10, and then we are going to apply the sum difference rule again. The limit is x approaches negative infinity of 2 plus, oh, let's make that 2 a little bigger, 2 plus the limit as x approaches negative infinity of e to the negative x equals. Now, of course, we have the limit of two constant functions. So that limit goes to 10. That limit goes to 2. Now, what about this limit? Now, let's think about this. We're taking the limit as x decreases without bounds, so very, very big negative numbers. In other words, I'm plugging very, very big negative numbers in for x. Negative 10, negative 1,000, negative 1,000,000, negative 10 million. But if I plug in negative numbers, I get a double negative. I get negative 10 million, because there's a negative sign there. But what does that mean? That means I get like e to the 10, e to the 100, e to the million, e to the 10 million. That's a massive number. That's going off to infinity. So what I get is 10 over 2 plus infinity. Which, of course, I know that 2 plus infinity is going off to infinity for sure. And then 10 over infinity gives me 0. So that tells me that what? That y equals 0 is here, let's just abbreviate this. Let's save ourselves some room. Horizontal asymptote. HA, horizontal asymptote. That'll save me some room for the rest of these. HA, horizontal asymptote. So we have two horizontal asymptotes, 0 and 5. That's the maximum. We can at most have two horizontal asymptotes. Here, let's look at the graph. What was the original? It was 10 divided by 2 plus e raised to the negative x. Yeah, we can see that as we approach negative infinity, those y values are going, it's like there's asymptotic behavior at the origin, approaching 0. So look, Desmos is actually rounding them to 0. They're so small. And that's only for x equal negative 30. So there, you can tell like they're getting super close to the horizontal axis. Okay? But then to the right, look at the y values. They're all going towards 5. In fact, Desmos here is rounding the y values to 5. They're not actually 5. They're like 4.999999, super, super close to 5. Okay? And if you want to, here, I'll put the horizontal asymptotes in. So we have y equals 0 as a horizontal asymptote. And we have y equals 5 is a horizontal asymptote. And what I'll do here is I'll say, hey, this one only is true for, let's say, x is greater than 0. And the other one's only true for x is less than 0. Okay, so there we have it. Two horizontal asymptotes. So sometimes you have two separate horizontal asymptotes. Sometimes you have one. Sometimes you have none. With polynomials, you have none. Okay, cool. Let's see what else we can get with example B. So B is another trig example, so that's kind of strange. You know, most of our examples we've been dealing with have been rational, so B is a little weird. But you know, we need to consider both limits at infinity. So we have the limit as x goes to infinity of sine 2x over x. Now here's the deal with this one. Don't overthink it. Just think about what do you know about trig, and then what do you know about the denominator. So with trig, we've talked about this before. Whenever you have a scalar multiple on the argument, on the input, it doesn't affect the range. So if you have sine x, we know that sine x bounces back and forth between negative, oh, that's positive 1, negative 1 and positive 1. Okay? So if you have sine of 2x, the range is still the same. Okay? That is, we didn't affect the amplitude. Okay? That being said, what we can surmise about the numerator, and here, this is not very mathematically rigorous, but I'll just say this. The numerator is some number. Here, I'll just do this. Number between positive 1 and negative 1. Like it oscillates. It goes back and forth. Negative 1 and positive 1. So negative 0, then negative 1, positive 1, negative 1, positive 1, negative 1, positive 1. And it's just some number like that. But the bottom is doing what? It's going off to positive infinity. As x increases, well, you just plug in 1 million, 10 million, 100 million. The bottom is growing. So here's the takeaway. The top is basically, we can treat it like a constant. It's stuck between negative 1 and positive 1. But the bottom is shooting off towards positive infinity. So for all practical matters, we can say that the top is a constant, although it's not a constant, but it's acting like a constant basically. And the numerator is growing, which means the limit has to be 0. Okay? By the way, this same argument works for the limit as x approaches negative infinity. Okay, so what's our conclusion? Our conclusion is y equals 0 is a horizontal asymptote. And the limit as x goes to negative infinity works the exact same way. Okay, we have sine 2x over x, and again, the numerator is basically some number that's trapped between positive 1 and negative 1. But in this case, the bottom is going off towards negative infinity. Well, if you take basically a constant, some number that's between negative 1 and positive 1, and divide by a negative 1 million, negative 10 million, negative 100 million, it's going to 0. So again, this tells us that y equals 0 is a horizontal asymptote. We already knew that. So in this case, we have one horizontal asymptote, which was one of our options. You can have 2, 1, or 0 horizontal asymptotes. Okay, let's look at the graph of this one. So we have what? Sine 2x over x. Now notice it is certainly bouncing back and forth. It's oscillating, but watch what happens the further you get out from the origin. The oscillations get gentler. See, it's bouncing back and forth. Yes, look at these y values. Those y values are getting closer and closer and closer to 0 when you go to the right, and the same thing is true when you go to the left. I mean, we're just over here at negative 80, and Desmos is already rounding the y values to 0 because they're so close to 0. So here at 73, out to 3 decimal places, the y value is 0.014, which is very close to 1, 0.013. And again, at about 80, Desmos starts rounding them to 0. So in both directions, we're bouncing back and forth, but very, very gently, because that denominator is making making the overall quotient go to 0 in both directions. So we have the same horizontal asymptote in both directions. Okay, what about example C? So example C is kind of what we were doing in the last video. In fact, it's basically the exact same thing. So let's take a look. We need to look at the limit as x goes to infinity and then negative infinity. So let's see here. We have radical 9x squared minus 2 over 4x plus 1. So we need to divide by the greatest power of x in the denominator. So we need to divide by x. So we do 1 over x, 1 over x. This is our specialized version of multiplying by 1. So we haven't changed the value of the expression. But remember, okay, I can easily multiply on the denominator, but on the numerator I have a constant. Sorry, I have a radical. So we have to think about this. Remember, how do we get to multiply underneath the radical? I need to have a radical right here. So I need to say multiply by something like this, right? Because we know this is true if x is greater than or equal to 0. And since we're taking the limit as x goes to infinity, yeah, we can say that's true. So this is just like we did in the last video. In order to get under the radical sign, we have to be careful. And so here on the next step, I'll say this is equal to the limit as x goes to infinity. Now on the bottom, we have 4x plus 1. We're going to multiply by 1 over x there. That's no problem at all. We're going to multiply by 1 by 1. Oh, I need more room. Sorry about that. Not enough room there. Equals the limit. X approaches infinity. We have radical 9x squared minus 2. On the bottom, 4x plus 1. Now on the bottom, we're just going to multiply by 1 over x, no problem. But on the top, we're going to multiply by the equivalent, because we know x is positive, which is radical 1 over x squared. So we get the limit as x goes to infinity. Now on the top, that's going to give us, if we multiply, radical 9x squared over x squared minus 2 over x squared. And on the denominator, that's going to give us 4x over x plus 1 over x. Now at this point, we can apply a couple properties, just like we did in the previous video. We're going to apply the sum difference property as well. Sorry, first we're going to do the quotient property to take the limit of the numerator and denominator individually. And then we're going to take the limit of the individual terms using the sum difference property. And then on the numerator, we also have to apply the composition property, which says, oh, by the way, that reduces to 4. I should have reduced these prior. Oh, that's all right. 4 plus the limit as x goes to infinity of 1 over x. Then up top, we're going to use the composition property to get inside the square root, which gives us the limit as x goes to infinity of what? 9 over x squared is 9, minus the limit as x goes to infinity of, well, 2 over x squared doesn't really reduce yet. So there you go. And now what can we say about these individual limits? Well, let's do these in a different color. Let's do them in red. Constant. That goes to 9, but make sure it's under the square root. 2 over x squared goes to 0. 1 over x goes to 0. 4 is a constant, goes to 4. So on the numerator, let's just make sure to not lose our constant because we took the limit under the constant. We have 9 minus 0. And on the denominator, we have 4 plus 0. So we have square root of 9 over 4, which of course gives us 3/4. This tells us that y equals 3 over 4 is a horizontal asymptote. Okay, now let's do the limit as x approaches negative infinity. Okay, so here we just got to be careful when we do that first step. Excuse me. Otherwise, it's going to be the same process. Here, let's save ourselves some room. How would actually? Nah, let's not do that. I don't want to confuse you. So let's not be. I'm not going to be lazy here. Let's start over. I'm going to leave this because we're going to need to readdress that. So let's see the other limit. Let's just put it right here. The limit as x this time goes to negative infinity of the original expression, radical 9x squared minus 2 over 4x plus 1. Now, the same thing, the initial step is true. We need to divide by 1 over x on the top and the bottom. Now, where you have to be careful is the fact that we are now taking the limit as x goes to negative infinity, which means we need to readdress this step. Okay? Readdress that step. So actually, let me leave the original there and say this. Square root of 1 over x squared equals negative 1 over x if x is less than 0. That is, if you know you're working with a negative number and you take the square, you square it, then take the square root, well, you're guaranteed to return a negative number. That's what we're saying there. So up here, and I'll just repeat how I did last time, on the next step, we're going to have to replace that top 1 over x with its equivalent so we can get under the square root sign. Because how it is right here, we can't combine these two. I can't get the 1 over x underneath the square root sign. Okay? So we're going to get the limit as x goes to negative infinity. So we're just going to rewrite the original limit, 9x squared minus 2 over 4x plus 1. Now we're still dividing by 1 over x on the top and bottom, but we're going to change the form on the numerator. We said that that is equal to radical 1 over x squared. But radical 1 over x squared, oh, sorry, I said something wrong. I'm going to fix it. 1 over x squared is equal to 1 over negative 1 over x. So right now, I have to put a negative sign right there. Otherwise, I'm not multiplying by the same thing. Because I know this reduces to negative 1 over x. The top does. So if the top reduces to negative 1 over x, then if I want to multiply by 1, the bottom has to also reduce to negative 1 over x. And so there we get 1 over 1. Okay? Let's make sure you follow that. The top reduces to negative 1 over x because we're only working with the negative numbers. Why? Because we're taking the limit as x goes to negative infinity. So if the numerator here reduces to negative 1 over x, then I have to multiply by negative 1 over x over here so that the overall right here, that simplifies to 1. Okay, so here we are. Distribute. So we get limit as x goes to negative infinity. Now on the top, I get radical 9x squared over x squared minus 2 over x squared. On the denominator, I get negative 4x over x, and then I get minus 1 over x, because I'm multiplying by negative 1 over x. Okay, and now if I apply, again, those properties in tandem, I'm going to apply the quotient property, the sum difference property, and the quotient property to take the limit of the numerator and denominator terms individually. I need the quotient property because, well, I have a square root on the top. So we have the limit as x approaches negative infinity. Now, if I reduce 9x squared over x squared, that's 9. Minus the limit as x goes to negative infinity of 2 over x squared. Then on the denominator, the limit as x goes to negative infinity of, okay, negative 4x over x is negative 4, minus the limit as x goes to negative infinity of 1 over x. Now, equals, let's see what we can come up with. Underneath the radical, there's a constant, 9 goes to 9, that limit. Here we have a rational function. The numerator is constant. The denominator is a quadratic variable. It goes to 0 overall. On the bottom, constant -4 means the limit is -4 regardless of what value we're approaching. And then we have the limit 1 over x. Again, bottom is growing, top is constant, goes to 0. So this leaves us with a radical on the top, 9 minus 0. And on the bottom, we have 4 minus 0. Oh, sorry, -4 minus 0. And that gives us with square root 9 over -4, which gives us -3/4. So that tells us that y equals -3/4 is also a horizontal asymptote. Okay, so we had 2 horizontal asymptotes. Let's check out the graph. Let's see here. What was the original? Was radical square root 9x squared minus 2 divided by 4x plus 1. Okay, so this weird kind of discontinuous function here, but to the right we said y equals 3 over 4 was an asymptote. Let's say that's only, since it's to the right, let's say x is greater than 0. And let's make it dashed like we usually do with asymptotes. Yep, looks good. Getting closer and closer to that asymptote, yep. And then what about to the left? We said -3/4. So let's copy that and say x is less than 0, and it was -3/4, and let's make that dashed like we usually do. Yeah. So we're definitely approaching -3/4 to the left as x decreases without bound, and we're approaching +3/4 to the right. So we have 2 distinct horizontal asymptotes, one to the left, one to the right. So sometimes we get 2, sometimes we get 0, sometimes we get 1. Yeah, it's just, it is what it is. We have to figure it out by evaluating both limits. Now, last example over here. I'm gonna have to scroll down here. Let's see. I'm gonna have to first of all make a note. Oh, I'll do some work onto the next page. It'll be all right. I'll erase it before we cover the next section. Now, what was the function? It was f of x. It was a rational function, which was what? 5 minus 3x to the 2/3 power. Divided by 3x minus 6. Okay, technique is the same here. Let's evaluate both limits to see if we get any asymptotes. Okay, limits at infinity. So we have, let's see, let's first do the limit as x approaches positive infinity. No rhyme or reason to that, which is what I usually do. So we have 5 minus 3x to the 2/3 over 3x minus 6. Okay, now what's the highest power of x in the denominator? What's x to the first power? So let's divide the top and the bottom by 1 over x. So multiply by, or divide by x, so let's multiply by 1 over x. And now let's distribute. So parentheses like so equals the limit as x goes to infinity. Now if we distribute here, what we get? 5 over x minus 3x to the 2/3 over x. On the bottom, we get 3x over x minus 6 over x equals the limit as x goes to infinity. Okay, now let's simplify. In fact, let's simplify. Let's simplify first. Let's leave it. We have 5 over x minus, okay, we have 3x to the 2/3 over x. What does that simplify to? According to properties of exponents, we have the same base, top and bottom. We subtract the exponents. 2/3 minus 1 is -1/3. This is going to be 3 over x to the 1/3. third, like so. Then we have 3x over x, that's 3 minus 6 over x. Lastly, let's go down here and use the sum difference rule and the quotient rule to take the limits of the numerator and denominator terms individually. So we get the limit as x approaches infinity of 5 over x minus the limit as x goes to infinity of 3 over x to the 1/3. On the denominator, limit as x goes to infinity of 3. Oh, let's fix that. 3 minus the limit as x goes to infinity of 6 over x equals, well, what do we get? 4 individual limits. That goes to 0 because the top is constant, the bottom is variable. Same thing here. That looks a little weird, but the bottom is still growing where the top is constant. Same thing here. The 6 is constant, the bottom is growing, and then that's just a 3. So we get 0 plus 0 0 minus 0, I suppose. 0 minus 0 over 3 minus 0. Of course, 0 divided by 3 is 0. That's not a problem. So we could say this implies that y equals 0 is a horizontal asymptote. Okay. Now, does taking the limit as x goes to negative infinity, does that really change anything? I don't think so, to be honest with you. Here, let's think about this. If we have instead the limit as x goes to negative infinity of 5 minus 3x to the 2/3 over 3x minus 6. Okay. We divide the top and the bottom by the highest power of x in the denominator, so 1 over x over 1 over x. There's no radicals here. Well, there's a cube root, but cube roots, that's fine. Cube roots have domain no real numbers, so we don't have to worry about anything there. So we don't have to really worry about that we're using negative numbers. We're taking the limit as x goes to negative infinity now. There's no special consideration there. So, the next step, in fact, we don't have to reinvent the wheel here. We can just say this simplifies. We can skip, I guess, like this step right here. We could say this simplifies to 5 over x minus 3 over x to the 1/3 over what? 3 minus 6 over x once we distribute and simplify. And then if we apply the sum difference rule and the quotient rule first, then sum difference rule, we get a quotient of those individual limits. The limit as x goes to negative infinity of 5 over x minus the limit as x goes to negative infinity of 3 over x to the 1/3 over the limit as x goes to negative infinity of 3 minus the limit as x goes to negative infinity of 6 over x. And just like before, all those individual limits are not affected by the fact that we're going to negative infinity instead of positive infinity. I mean, the fact of the matter is, in that first limit, the bottom is growing. Whether it's towards negative infinity or positive infinity, it's growing, and the top is constant, goes to 0. Same thing on the second numerator limit on the right-hand side. The top is constant, but the bottom is growing, goes to 0. Same thing here, that's a constant. So it doesn't matter what we're approaching, negative or positive infinity, it approaches 3. And then same thing here. The denominator is growing, whether it grows to negative infinity or positive infinity doesn't really matter. The top is constant, so it goes to 0. And so we are going to get the exact same answer of 0 minus 0 over 3 minus 0 equals 0, which implies the exact same thing, that y equals 0 is a horizontal asymptote. Here, let's check out the graph and make sure we're correct. Let's get rid of that function. And now we have what? 5 minus 3x to the 2/3 over 3x minus 6. Hope that is not right. 2/3 over 3x minus 6. Okay. All right, so I'll be the first to admit it doesn't look very good, promising at first. But I think this might be a situation where the function very slowly goes toward negative or positive, or goes towards 0 as you approach negative infinity. Yeah, I think so. If I zoom out here, what's the y value? 0.192. Okay, so the x value is like a negative 130. The y value is 0.192. That's getting close to 0. What about over here? So here the x value is about 200. The y value is getting close to 0, negative 0.164. Here, let's verify that. Let's do like f. Here, let's make a table. Desmos uses tables. Here, click this little thing, do a table. And change that to an x, change that to an f of x. Then put in values. 10, 100, 1,000, 10,000, 100,000, million. Yeah, those y values are going towards 0. So that's as x goes to positive infinity. Now to negative infinity, just make them all negative. Let's see what happens. Negative, 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 negative. Yeah, you can tell the y values in both directions. It's kind of hard to tell the graph, especially if you're close to the origin. If you're close to the origin, it doesn't necessarily look like you have that the graph is going to 0 in both directions. But if you look at the table of values and if you zoom way out, yeah, you can tell that it's going to 0. Okay. By the way, the table feature is a pretty handy function of Desmos. I don't know if I've shown you that before, but if not, all you have to do is click here, add a table. Now you do have to, if you want to use the function you have labeled up here, you have to have a function called f or g or whatever you want to call it. But you have to have f, put an x right there, and put f of x there, or whatever you call your function, g of x, f of x, whatever, and it'll generate the table values for you real fast. A lot faster than a graphing calculator for you. Okay? So yeah, there we have it. Solution's definitely correct. Horizontal asymptote at the origin. Although it doesn't appear so if you're really close to the origin. Okay? So that wraps up this section. We did a couple of videos on limits at infinity. And before that, we talked about infinite limits. And before that, we talked about all the different ways to find limits analytically. In fact, that was this whole section. These are all analytic limit methods when you're multiplying by special versions of one and using the sum difference property and the quotient property and the composition property. Those are all methods for analytic limits. We're using the analytic methods toolbox and all these things like multiplying by special versions of one and all that kind of stuff. These are the methods that we really need to hone as we go forward, because these will be the methods we want to use in the next chapter, in the next chapter, the next chapter, whenever we're doing different applications of calculus going forward. Doing these things called derivatives and integrals and curve sketching and that kind of stuff. This is what's really important, is these analytic methods. So in the next section, we'll change gears a little bit. We'll talk about a concept called continuity, which is also very important, but we'll obviously discuss that more there. For the time being, let me know if you have any questions. More than happy to help. I'll catch you in the next video.